Hello. Today we're going to talk about ultra reliability and channel characteristics in cluttered industrial environments. My name is Fredrik Tufvesson. I'm professor at Lund University in Sweden, and this is joint work together with colleagues Harsh Tataria, Sara Gunnarsson, and Stefan Malkowski. Let's first start with the question, why do we care about cluttered industrial environments, and why can we not use all the experience and knowledge that we have had before when it comes to the channel properties? Well, basically, the reason is here. Industrial environments, they might be very cluttered, and this is one example. And for example, here we have robots going back and forth. We have those AGVs, or the mobile robots, going in a more random fashion. We have a lot of equipment, both here to the left as well as to the right, and everything is basically made of metal. So it's quite a complicated propagation environment that we have there. And in order to create reliable communication, how can we actually do it? And actually, reliable communication is not a problem. That we know how to do. The problem comes with a combination of ultra reliability and reliable communication, because then we cannot afford retransmissions. We basically have to prepare everything in advance so that we know that if we are using, for example, millimeter wave communication, we need to have parallel beams to the different clusters in order to have them ready when one of them disappears, for example, due to shadowing. At midband, the situation is somewhat easier there, because there we can rely more on the diffraction around the corners. But we'll see. As I mentioned, cluttered environments, they create challenge and also some opportunities. There are many reflecting objects, and but at the same time, we can also experience some shadowing from this equipment. Depending on which kind of industrial process we have there, it can be quite a dynamic environment, either due to the process itself, that the machinery is moving, or we can have, for example, that the transmitter or the receiver is moving. And also, it's possible that we have interference to the plant that we cannot tolerate, or from the plant that we have taken into account. All in all, challenging, but also quite interesting environment. And let's have a closer look at what's actually going on there. Right now, we're in the middle of an industrial transformation. The factories of today, they are dominated by wired technologies. They're somewhat fragmented, and they are actually quite static, because it's really hard to reconfigure the manufacturing process due to all the cabling that is there. It's also, there are a lot of protocols, and it's we need to have some translation between those protocols in order for different parts of the factory to work together. What we're hoping for with Industry 4.0 is that we can replace many of those wires with wireless connections. And with the wireless connections, we get much better flexibility, so that we actually can reconfigure the manufacturing process much easier, and thereby, at the end, also get larger productivity. If we now focus on the channel characteristics that we have in this large semiconductor factory where we have done the measurements. So it's quite a large clean room. So it's roughly speaking, it's 50 by 100 meters, filled with equipment. They're producing wafers there. And so it's located in Reutlingen in Germany. What we are trying to investigate is how to really do successful 5G deployments in industrial environments like this, and how reliable can the radio coverage be on the factory floor with all the machinery and tools in midband at 3.7 gigahertz, as well as high band, in this case 27 gigahertz. And what is the specific propagation behavior? Specifically, we want to know what is the received power distribution across the factory floor, what is the role of shadowing and blocking, and what are the dominating propagation processes, so that we can recreate this ultra reliable communication. So for the measurements, we've used two systems. For the midband, we've used the Lumami, Lund University Massive MIMO testbed. It's operating at 3.7 gigahertz. It has LT-like transmission parameters based on OFDM. It has a center frequency of 3.7 and a bandwidth of 20 megahertz. There we have 100 transmit and receive antennas, and they all work in a coherent fashion. For the high band, we have used the channel sounder that we have developed here at Lund University. For the measurements, we have used 1 gigahertz of bandwidth, though the sounder itself supports 2 gigahertz of bandwidth. It's the switched array sounder. So we have the receive array here, we have the transmit array here with all the antenna elements. We have 128 ports at the transmit antenna. We have 256 ports at the receive antenna, and we are switching through all those antenna combinations. That means that we can, as post-processing, do coherent high-resolution processing to really see the details of the channel. With this measurement system, we also have video modulators to make sure that everything is working coherently. We have the control PC here and here with the baseband processing. Here we have RF converters and the two antennas over here. So in the factory, the measurements might look like this. So we have the transmit system here. We have the receive system over here with a transmit array, a receive array. We're doing video documentation, a lot of photos to make sure that we know afterwards what's going on there. In this environment, we also have, for example, the linear robot going along here. We have the mobile robot going in more random fashion, and we have humans walking. And everything is done during operation, so in actual manufacturing. So it's, I would say, quite unique to get such an opportunity to do it in a live plant like this. Could also point out that the floor here is made of metal. The roof is basically made of metal. All the machinery here is mostly metal with some plastic parts as well. For the millimeter wave, the directional estimation process that we're doing is that we have calibrated receive and transmit arrays. They're both calibrated in amplitude and phase, which means that we can use high resolution properties and that we can extract the power, the delay, incoming, outgoing angle, Doppler and polarization with the high resolution. For the processing, we are using Remax, which means that we can both estimate the specular components as well as the dense multipath components. We start with some initial estimates for both the specular components and the dense multipath through a global grid search method, and then we further refine those estimates in an iterative process. So let's start at high band and with looking at some impulse responses. So we have now the transmitter over here, we have the receiver over here. So it's a planar array at the transmit side looking in the forward direction towards us. And this receive array, it's a circular stacked array so that we actually can find all the components coming with different azimuth directions. And should now look at two impulse responses, one a little bit closer. I mean, here it's only 4 meters between the transmitter and receiver. And then we have another, this is the side view. And as you see, there are a lot of equipment quite close to the receiver in this case. We'll also have another look at an impulse response where we've moved the receiver 10 meters further away from the transmitter. But let's start with this close one. So here is the impulse response. We have the received power level here going from -35 and down to the noise floor here, roughly at -88 dBs. We have the propagation delay here, and it's, as expected, quite dense channel impulse response that we see. Here we have a line of sight dominant region, we have some specular reflections, and then we have some weaker diffuse multipath components at the end of the impulse response. If we look carefully at this line of sight cluster here, it's not just a single component. We have a line of sight, but then we also have somewhat weaker components with somewhat larger delays, but with this high resolution. I mean, now we should remember that with the 1 gigahertz bandwidth that we're using, we have 30 centimeter resolution in propagation distances. And then we have the angles there, which means that we really can separate the individual multipath components in this case, which makes those measurements a bit unique, I would say. If you go further down, of course, we get a shift in the delay, but otherwise it's quite interesting how similar those impulse responses are. We have a line of sight cluster. So here the black one is the second impulse response that we have measured. And the structure is actually the same. We have the line of sight cluster, we have some individual stronger multipath components, and then we have a lot of dense clutter, just a little bit above the noise floor there. Let's look at some dynamic aspects. So we have the transmitter here at the end of the corridor, looking over the corridor like this. We are doing the measurements now along this corridor here. And the starting position is here. And you can see the transmitter array there. We have the receiver array over here. And then we have shelves with a lot of plastic boxes here. And then we have another bunch of shelves here. And you see those shelves, they are all around here. And if we look carefully now and at the parameters that we extract. So here we have the azimuth angle of arrival versus measurement time. And here we have the path gain versus measurement time at high band. And now we have moved, depending on scenario, between 0.5 meter a second and meter a second, which means that looking at the components here, some of them have quite a limited lifetime, I would say. I mean, if we take this component here at 35 degrees, I mean, it has some weak contribution here until it becomes strong at 8.5 seconds, and then it remains visible for another 4 seconds, but then it disappears. So this particular component has a lifetime of about 2 meters. And there is another component here that takes over, has also a lifetime of 2 meters. Some of them, they have longer lifetimes. Some of them are really short, but the multiple components, they come and go, and they can die pretty fast, as you see. If we look at the received power, it's actually varying quite a lot. And I mean, the mean power is decreasing, and as expected, since we're increasing the propagation distance between the transmitter and receiver. But you can also see, if we take a look at all the measurement points here, that the power is varying. It's varying with the power of, I would say, plus minus 5 dB or so, which is quite interesting. Let's look at some more detailed properties when we have shadowing. And here is shadowing by those mobile robots. So we have the transmitter over there, we have the receiver over here, and then we have line of sight. Then the robots, they are coming. And at this particular moment, I mean, we still have the line of sight, but they're shadowing on 2 of the sides, and then they are disappearing, they're traveling in that side. So let's have a look at how the impulse responses look like, and also at the angular characteristics. So here we have the line of sight scenario, no blocking. We have the line of sight cluster again. We have some specular components, 1, 2, 3, and 4 here. We have another cluster 2 of pretty strong components. And then when the robots are moving, and I mentioned that still we have the line of sight, there. So you can still see the line of sight cluster here, but this cluster 2 has disappeared. The specular multipath component 1 and 2 and 3, they have also disappeared. So in order to create reliable communication here, I mean, once we get such a shadowing event that we have here, we cannot start looking for what are other possible clusters, but we need to have those clusters already active and use them in our communication so that we have parallel beams and that we can either combine in a coherent way, or once one is disappearing, we need to have the other one ready. We cannot just start searching them, because then we will lose communication for a while. Then later on, when the robots, they continue moving to the right, and then those clusters, they reappear again as expected. So here we can see the line of sight cluster, we have the cluster 2, and we get some of those speculum components back, but a few of them are still shadowed by the robot to the right. If we look at the angular characteristics, so we have the 3 cases, A, B, and C, and here we have the angle of arrival versus propagation delay. And we have cluster 1, we have cluster 2, and then we have some of those other strong specular components there. And if we now move to case B, where we have the robots, and then we see that they take away completely cluster 2, they take away some of those specular components. So basically what remains for us for communication is the line of sight cluster, which is quite good in this case. And then we have some somewhat weak but existing multipath components there. Now when the robots, they continue to travel, then as mentioned, cluster 2 reappears. We also get some strong multipath components back, and we still have those weaker ones with a somewhat longer propagation delay. So let's now look at midband. There, so here we have a similar shadowing event. So we have the receiver over there, we have the transmitter here at the back, and then we see that one of those robots, mobile robots, they're coming and it's traveling to this side. And if we look at what happens with the received power, now in this case we are using, so we have coherent combining from all the 100 antennas, which means that we get some really good diversity gain there. So it's, and if we look what happens with the channel power, here we have the horizontal polarization, we have the vertical polarization, line of sight, and then they are approaching the line of sight so that we get a somewhat oscillating behavior, and then we lose some power, but it's actually not so bad. We are losing around 5 dB or so for both the vertical as well as the horizontal polarization. And then they are coming further to the right, to get the line of sight, but still with some interaction, as you can see in the oscillating behavior that we have there in the received power level. But all in all, it's actually not so bad. If you look at another case, another example where we also have, I mean, we have a robot blocking the line of sight similar to what we had to the right, but also after some time here, we also have a human coming and blocking the line of sight basically totally. But due to the coherent combining, then we can actually get a quite stable connection. And I mean, the power loss of a few dB that we have here can easily be managed with the system. So let's now go to a somewhat more complicated situation, blockage by equipment. So here we have a similar, another part of the factory. We have the base station array over here, and then we have the receiver moving in this corridor. But what you don't see here is that we have also, we can go behind the equipment here and there and there and there. So if we follow the track of the user equipment, it's going behind and then coming out to line of sight, going behind the next one, coming out, going to the next one, and so forth. The width of those corridors, it's varying between a meter and a meter and a half. And the equipment, as you say, it's roughly speaking 2.5 meters tall. So we have the base station over here. The UE is moving in and out of those corridors down to the end here. And here you can see a picture from the base station, and you see that it's actually quite a narrow corridor that we have in this case. So let's look at the power that we receive. And at midband, actually the channel hardening provides quite good reliability. So if we start with the channel gain that we have here to the left, we have the vertical and we have the horizontal polarization. And then we are, from the line of sight, then going into the first corridor, coming out of the first corridor, going into the second one, coming out of the second one, going to the third one, and so on. And as you can see, the loss we have, the difference we have between the line of sight and the full blocking by equipment is not so bad. We lose 7/8 dB, but it's not too bad, I would say. Even more interesting is the channel hardening effect that we have with massive MIMO if we do maximum ratio combining. So here, what we have here, we have the frequency point. So it's a 20 megahertz channel bandwidth that we have, and then we have 100 pilots. And here we have the time samples when we do a scan behind one of the equipment, one of those metallic machines that we have there. And as you see, here we have a single antenna. Here we have the combination of the 100 antennas after maximum ratio combining. And as you see, the fading has almost entirely disappeared. So we're going from the line of sight, and then we are going behind the machinery, and we stay behind the machinery here, and we have quite many samples here. There is not a single sample where we lose more than 2-3 dBs. Compared to the single antenna case, that we have here, there we have the standard fading between 20 and sometimes 30 dB down from the mean power. So it's actually, I would say, very promising when it comes to providing ultra reliability with the midband channels, where we have a lot of diffraction, with proper combining, with the many antennas. We actually can get quite nice channel properties, and shouldn't be a need for retransmissions there. If we look at the distribution of the channel gain, so here we have the comparison if we have normalized them. So we have the single antenna case with quite large variations, and then we have the massive MIMO case with maximum ratio combining. And as you see, the deviation from the main is just a few dBs up or down. Here is the line of sight region. That is why we have a few samples there. Also, if we look at the single subcarrier, so now it's a narrowband 15 kilohertz carrier that we have, and then we look at the time evolution while we are scanning many points behind the machinery there. And you can see that there are hardly any channel variations, a few dB up and down, and that's it. Then we couldn't resist. What happens if we distribute the antennas, and instead of having a co-located array, we distribute the antennas even further? And so now we have an array that spans 10 meters, basically. So we have the base station here and now cable connection. And we try to have as random orientation and location of the antennas as possible. As seen, we can actually even further decrease the variations, because now the likelihood that we have a few good antennas there is actually quite high. And doing the same comparison, going from the line of sight to the non-line of sight, line of sight, non-line of sight. Now, I should also point out that not all of the antennas are in line of sight at the same time here, but we can be pretty sure that all of the antennas are in non-line of sight in the shadow zones here. But here the difference is they are rather in the order of 3 to 4 dBs. So with such a distributed configuration, for sure, I think we can get quite good and stable conditions. If we now look at the high band and the same blocking, so a similar corridor or the same corridor, we have the base station array here, and it's now looking into this corridor here, and we are moving the UE from here to the right and then to the left like this. So it's going from non-line of sight, obstructed line of sight, obstructed line of sight, non-line of sight. And you see it there. And now the situation is quite different. So if we start here in the shadow zone, we can say that we have quite high loss there due to blockage by the machinery. And when we go from the shadow zone and the deep non-line of sight zone until the obstructed line of sight zone, we gain in the order of 20 dB. And then going to the line of sight, we gain another 15 dB, so that the difference between the line of sight that we have here and the non-line of sight here is in the order of 35 dB, which is quite different from the situation at midband. And then when we go out, go further into the obstructed zone here to the left, it's we're back again. We are losing 10-15 dB. And as you can see, I mean, we still have some variations here in the power in the shadow zone there. So here the situation is definitely more tricky. I would say that we had to be more careful in the deployment when we want to create this reliable communication. Maybe it would have been a somewhat different situation if we could have put the base station antennas up in the ceiling or something like that, because it's really shadowing here affects the UE quite severely. One could think that with all of those metallic objects there that we have, we should always have some good possibilities to use the reflections. And I was a bit surprised seeing that that is not the case. We have a lot of scattering, that is true, but to have effective reflection is not the same thing as scattering. So to conclude, we have performed some unique measurements in a real challenging industrial environment, and it's under operation. And I would say that the results show quite promising behavior when it comes to what are the possibilities to create ultra-reliable low latency communication. Especially at midband, the many antennas used in MIMO provide channel hardening so that we have hardly any channel variations. The fading is more or less gone both in time and in frequency. At high band, the situation is a little bit more challenging, I would say, requiring a more dense and careful deployment. So still, this is ongoing work. Next step is detailed modeling of this channel behavior. And both at midband, looking more into the channel hardening and how we can use that in the best way for ultra-reliable low latency communication, and looking more into diversity aspects of the high band channel. So this is one part of the project 5G Smart. So we are focused now here on the Bosch factory in Reutlingen, where we are using 5G for enhanced semiconductor automation. There are two other trial sites. One in Aachen, Germany, where we are using 5G for enhanced industrial manufacturing. And then we have a site in Schist as well, where we are looking into enhanced industrial robotics. It's not only about communication and channels, but for this to work out, we also need to consider business models. How can we get a good I would say ecosystem involving both the equipment providers, the owners of the plants, the operators, and the system integrators, and that is also parts we are looking into. And then we're looking into some also new features for 5G, like time-sensitive networking and using more cloud-based coordination of the manufacturing processes there. But with that, I would like to say thanks for your attention and looking forward to questions. Thanks.